of a function now, the limit of a function, right? More mathematical. Intuitively, the limit of a function can be found or can be understood from its graph, Later, I will show you another technique. It's using tables. But first, let's try to understand what should be the limit of a function by looking at its graph, okay? Example 1, let f of x be x squared minus 4 over x minus 2 is called a rational function, okay? Whose graph is shown below. This is the graph of this guy. A line, professor? This in precalculus, when I graph these things, I saw curves. A line with a hole? Well, guys, turns out this is a special rational function. The reason it shows a line is because of this. We're going to write it on the side here, okay? So on the side, we're going to use this later, right? But on the side, notice this guy, when simplified using factorization, which is something that we will see in details later. I'm just going to give you this in advance for you to believe that this is just a line. It's just this, x plus 2. And isn't it the graph of y equal x plus 2 a line? It is, right? It is. Meeting at this point, the y-intercept 2, right? A slope 1. Yeah, so it is that. Now, in case you still want to confirm, make sure, right, 100% that this is a line, the graph of this, even though if it's given, right? Well, you can graph it, right? Y equal x squared. This time, yeah, let me just use this, x squared minus 4. Here the trick, highlight, slash, and then you will be able to write the denominator x minus 2. It is a line, right? Now, guys, I said, right, this grapher is a basic graph. Doesn't show this hole. But if you go to 2, which is an important point where this denominator is 0, you will get to see the hole. We got 2, you go up here, there is a hole there, undefined. And I will give you now an explanation why it's undefined, but you can see, right? That's the graph. It's a line with a hole there. When you click with the mouse at x equal 2, you go up to the graph, you will see it there. Now, why there is a hole there? Well, because notice that if you attempt to evaluate this function at this value 2 here, notice 2 squared minus 4 divided by 2 minus 2. 2 squared is 4. 4 minus 4, 0. 2 minus 2, 0. 0 over 0, undefined. Undefined. That is the reason why there is a hole there. All right. So, right? So at 2, undefined. But the rest is well behaved because it's just this guy, y equal x plus 2, right? So it's a line. Very good. Now, knowing that it's a line, let's talk about the limit, right? The limit of this function as x approaches 2. All right, the fact that this function is undefined at 2 doesn't prevent me from investigating what happens with the function in a neighborhood of 2, right? When I am very close to 2 from the left, when I am very close to 2 from the right, right? And this is what the limits deal with. They deal with the trend, the behavior of the function in a neighborhood of a point, not at the point, because you can see that at the point, there's no way to compute this output value, right? Yeah. So mathematicians figure this out. They said, okay, what happens if we approach 2 first, say from the left, if we consider input values very, very close to 2 from the left. Well, if you look at the output values, right, are approaching to the number 4, right? Why 4, Professor? Well, 2 plus 2, 4, right? If you look at this as a line, this is a 4, right? And also you can see that in your Desmos grapher, if you trace the line, you will see that the value that appears here is 4. Now, that is what happens if you approach 2 from the left. But what about approaching 2 from the right now this way? Well, if you consider input values very close to 2 from the right, 2.1, 2.11, the output values now up here, they will come down to this value 4 also, right? Right, you see it? Comes down to 4. So mathematicians, they write properly or formally this as follows. They say the limit of f of x as x approaches 2 from the left, they put this negative sign on the top, is from the left, approaching 2 from the left, is equal to 4, right? And the limit of the function, the output values, right? The limit of the output as x approaches 2 from the right. For that, they use the plus sign on top of the number. This approaching 2 from the right is also 4, right? 4. Approaching 2 from the left leads to output values approaching to 4. Approaching 2 from the right leads to output values approaching to 4. This is what mathematicians call convergence. We are going to the same destination, right? 4, 4. If that happens, mathematicians write as a conclusion that the limit of the function f of x, which is this rational function, right? As x approaches 2, they don't write plus, they don't write minus. They mean you're approaching simultaneously from the left and from the right is equal to 4 because these two guys match, right? 4 here. You follow, guys? So at least if they give you the graph, it is possible to figure out the limit of a function, right? As you approach some input value, in this case was the number 2, right? The number 2. The limit of this function as x approaches 2, simultaneously from the left and from the right, leads to 4. So, because 4 here, right? So that's the idea of the limit when you look at the graph of a function, right? Deals with the behavior of the function on the neighborhood of this input value, right? Not precisely at that input value. At that input value, this is impossible to compute the value of the function, right? That was example 1. Example 2 now. What happens if there is no convergence? What happens if when you go to the left, you are going to some real number, when you go to the right, you're going to some other number? Well, let's explore that. Let's consider this other function now. G of x equal absolute value of x minus 2 over x minus 2, whose graph is shown below. The graph of this function is this. Horizontal line here on the right of 2, horizontal lines here on the left of 2. Also, how you figure this out? Again, guys, there is always explanation behind things, right? X minus 2 over x minus 2. If this is positive, this leads to x minus 2 over x minus 2 equal 1. This justifies this piece. But if this is negative, its absolute value is its opposite, right? It's opposite, the opposite of this guy. You saw this in pre-calculus, right? This cancels, but this is negative 1. This is the explanation, right? So, yeah, so we have an explanation, right? We'll go over this in detail, but now the graph is given, right? And again, if you guys don't see this clearly, use your tools. Use this Desmos basic grapher. A graph y equal absolute value. Where is absolute value, Professor? Well, here, absolute value is here, apps, functions, apps, or just here, I found. Absolute value, what? X minus 2, right? And then again, right, the trick, come out there, highlight, slash x minus 2. I'm giving you all these tools, guys, because calculus unless you have all your tools, unless you are checking constantly what things should be, it's not going to make sense easily to you, right? So use your tools. Look here, this is the graph, right? This is this piece, this is this piece, right? Great. Professor, I don't see the holes. I explained to you guys, it's a basic graph. When you click in there, you will see the holes, two undefined, right? Why two undefined? Well, because if you attempt to compute the output value of this function at the number 2, you will quickly see that you get yourself in trouble, right? Because look, this will be absolute value of x2 minus 2 over 2 minus 2, 0, absolute value of 0 over 0, 0 over 0 again, which we call undefined, right? Undefined. Trouble there. But now, the fact that we cannot compute this function at x equal 2 shouldn't prevent us from investigating what happens on the neighborhood of the input value x equal to, right? On the neighborhood, meaning on the right or on the left, right? Before reaching 2. And let's do that again as we did before. If we approach 2 from the left, meaning 1.99, 1.999, values like that, right? The output values will be headed where? Anybody could tell me at this point, where are we going when we approach 2 from the left here? As x approaches 2 from the left, remember this means from the left, where are the output values going? Yeah, I see. Yeah, Oscar, excellent, right? Yeah, aren't they going here, right? To -1, that's it. Excellent, excellent, excellent. Very good, guys. Yeah, that's the idea, right? When you have the graph, you can trace where the output values are going and more or less -1. Very good, Sarah. -1, right? Excellent, this guy, right? And now, if we do the same from the right, to approach 2 from the right, where are the output values going? Look. In the chat. Yeah, Sarah, very good. Excellent, excellent. You got it. Yeah, this should be 1, right? If x approaches to 2 now from the right, look at the output values, 1. But now, when we look at the overall, right, conclusion, this guy is going to -1 from the left. This guy is going to 1 from the right. There is no convergence. They're going to different real numbers. Whenever that happens, mathematicians, as a conclusion, they write that the limit of the function g of x, which is this, as x approaches 2, should be considered undefined. They write this, DNE, DNE, does not exist. Does not exist, right? Does not exist. Yeah, not to be confused with DNA, right? It's just in forensic science, right? But here does not exist. Yeah, very good, very good. Yeah, so whenever there is no convergence, excellent, Sarah, DNE, right? DNE, right? That even in the homework they will ask you to do this type of things, does not exist. Yeah, there you go. Excellent. Only when there is convergence, you say that there is a limit. Now, based on this, mathematicians formally define the limits as follows. We will say that the limit of a function f of x as x approaches some real number a will be equal to L if the output values of the function approach L as the input values approach a from the left and from the right simultaneously, right? You're going to the same real number. Otherwise, we will say that the limit of the function as x approaches does not exist, DNE. Someone wrote something on the chat. Yes, of course. Yes, Sarah, very good comment. Sarah is saying, right, instead of DNE, can we say does not exist? Yes, but remember, mathematicians are minimalists. They like to shorten things out, right? So instead of writing phrases, they prefer this. So in the homework, they will say, right, if your limit does not exist, type DNE, right? But if this written your assignment, you can write this, right? It's okay, it's the same. Very good. All right, and the formal definition for one-sided limits should be the limit of a function f of x as x approaches a from the left. Why do you know, Professor? How do you know this from the left? Well, look at the negative sign on the top, right? This from the left is L. If the output values of f of x approach L when the input values approach a from the left, right? From the left. Maybe I should highlight this for you to remember, guys, important this with this, from the left. And similarly, a limit of f of x as x approaches a from the right is equal to L if the output values of f of x approach L when the input values approach a from the right. Professor, how do you know they're approaching L from the right? Because of this positive sign on the top, right? Yeah, right? These are called one-sided limits, right? Yeah, very good, very good. Excellent, excellent. Yeah, great. So now let's see. Let's continue here. Let's close and open this again. Very good. So now let's go over some worksheets, right? Yeah, we're asking for worksheets. Yeah, these are important worksheets, guys. These are well-chosen questions that you need to master in order to have like a base for you to face the examinations, even the homework, right? So let's do it together. For example, here, the first question, I'm gonna ask you to think about this. It says, find the limit of this function, whose graph is this, right? As x approaches -1. What is this limit, right? And together with that, they want you to evaluate the function at f x equal -1, input value -1. So these two things. Anyone can figure this out? I will give you some time. And hint, guys, approach -1, which is here, right? Which is here. -1 is there, right? From the left and from the right, right? Approach and then make your decision, right? Approach from the left, then from the right, and figure out what should be the limit, right? If you see that it's convergence, if you're going to the same destination from the left and from the right, yes, there is a limit, and the limit is precisely that number that you're sort of sandwiching right there. If not, you have to say the limit doesn't exist. Yeah, very good, very good. Yeah, great. Yeah, I will always give you hints, guys, because we're starting, right? So, yeah, anybody can figure out the limit and then the actual evaluation. For the actual evaluation hint, look at this guy. For the actual evaluation, look at this solid circle there. Yeah, this is the actual evaluation, but the limit is different, right? The limit doesn't deal with what happened at the point. It deals with what happened in the neighborhood. Yeah, I see some answers. Oscar, yeah, very good. Yeah, you made my day, Oscar. Sarah, also excellent. Yeah, Win, NG also, very good. Excellent, guys. Very good. You figure this out. Let's do it together. Okay, for the limit, we said we have to travel along the function from the left, from the right, approaching to -1. If you approach -1 from the left, look, the output values are going here. But Professor, what is that value? Is this guy? Well, they're saying, right, that this point A has coordinates. It's here, look, it's -1, 4/5. So the partner of -1, via the function is 4/5, 4/5, right? It's there. That's 4/5. So approaching from the left, -1 leads to output values going to 4/5. Approaching from the right, right? This from the left, this from the right, leads to output values approaching 4/5. So the limit should be 4/5, right? 4/5. Excellent. Yes. Because it's convergence from the left, from the right. Now, the evaluation cannot be done over this hollow circle. For that, you see there is a solid circle here, down here, right? And that solid circle is clearly -1 here. It's a tricky question here, but Once you understand what to do, should be fine. The negative one, right? This guy is here. Great, excellent. So making the answer this. Excellent. Let's go ahead. Let's talk about the next. Can you try this now? It's a different one. It says find the limit of the function whose graph is this, right? As x approaches 0 from the left, right? Let's write it out. Limit of the function f of x as x approaches 0 from the left. How do you know, professor, from the left? Because of this negative sign, right? Figure this out. And also they want you to figure out what is the limit of the function whose graph is this as x approaches 0 from the right, right? From the right. So hint, trace very close to 0, which is here 0, right? What is happening with the output values if you approach to 0, which is here, right? From the left and from the right. This is 0, right? See where the output values are going from the left and from the right on the neighborhood of 0, right? Yeah, great. And then answer. From the left, where you're going, from the right, where you're going. Yeah, these are called one-sided limits, right? One-sided limits, yeah. Let's see number 2. It's tricky, a little bit tricky, guys. So, yeah, very good. Grace, very good. Yeah, Adriana, excellent. Sarah, yeah, Oscar, very good, guys. Yeah, excellent. I see you guys are picking it up. Great, right? If you approach 0, which is here, input-wise from the left, output-wise, you're going up here to 3, right? 3, so this is 3. And if you approach input-wise to 0 from the right, the output values are coming down to this guy, which is -1, right? Yes, excellent. So therefore, answer has to be this. Excellent. Very good, guys, very good, yeah? Yeah, now if they ask for the limit without this minus, without this plus, that would be, doesn't exist, that limit, right? But they're asking for sided limit, right? From the left, from the right there. Okay, great. Another one here. Let's see if you can do this so we can move on, guys, because we're gonna cover more. Yeah, try this now. Good. Find the limit of f of x as x approaches 0 simultaneously, right? From the left and from the right. Be careful there, okay? Yeah, it's a tricky question. And together with this, figure out what is f evaluated at 0. F evaluated at 0. First the limit and then f evaluated at 0. Hint, try to approach from the left to 0, see where you're going output wise, and then do the same from the right, see where you're going output wise. And if there is convergence, yeah, you can have a limit. If there is no convergence, you say it does not exist, a limit, right? Yeah. And Sarah figured this out. Excellent, Sarah. Excellent, good work. Yeah, very good. And for the evaluation, always look at the solid dot, right? Solid dot here. Excellent, guys. Yeah, very good. Yeah, we're doing this with a graph. Then we'll do it with tables and later on with algebra. Okay, so let's do it together, right? For this limit to exist, I have to see what happens if I approach 0 from the left. If I approach 0 from the left, I'm going down to 0. If I approach 0 from the left input wise, look, the output values are also coming down to 0. There is convergence. For the left, you're going to 0. From the right, you're going to 0. So if there is convergence, yes, the limit exists. Not only that, is equal to this value, 0, right? Great. And the evaluation, I cannot do the evaluation here. It's a hollow circle. Instead, I look at the solid circle. The solid circle is located at 6 units up here. So this should be 6. Excellent, right? 0 and 6 in that order, right? Excellent, guys. Very good. One more here. I think you can do it at home. Let's move on. Yeah, let's move on with other topics, okay? So let's see. Let's leave this here and then let's move on. See there? Yeah, do this at home. Have some fun there. All right, next, what if the graph is not given? What if they ask you to compute a limit, but they don't give you the graph, or the graph is very complicated to come up with, right? So let's say they give you this, find the limit of sine of x over x as x approaches 0 using another method. This other method is called using tables. I will show you. It's a very, very universal method to compute limits. And it's kind of strong because it always works. It always works. If you create a table and look at the output values, where are they approaching, then you will get to see the limit, okay? Even if you don't have the graph. So let me show you. And then we'll go over some examples on worksheets. Solution. Notice if you look at this guy, 0, right? 0 here. And you try to evaluate at 0, what happens? Unfortunately, sine of 0 is 0 over 0 undefined, right? Undefined. So there's no way to evaluate this function at 0. But however, I don't require this for a limit, right? For the computation of a limit, because limits deal with what happens on the neighborhood of 0, right? Not necessarily at 0. Okay, so this gave mathematicians idea of this method is called constructing a table and kind of trying to see where the output values are going. So create a table and choose values that are very close to 0 from the left. What values are close to 0 from the left, Professor? Well, for example, this guy, right? Start with, let's say, negative 0.1. It's very close to 0. Something even closer to 0, negative 0.01. Something even closer, 0.001. Right? And do the same from the right. 0.1 is a input value very close to 0 on the right. 0.01 even closer, 0.001 even closer, right? And then using your calculator, get the output values, the corresponding output values, and then we will see where these output values are going, right? So that's that. So get your calculator. The decimal scientific calculator that I'm using is here. I gave you a link, right? In case you need it again, just let me know. But when you do the computation, guys, make sure you're working in radians. Why? Because look at this, x doesn't have a little circle on the top. This is x radians, sine of x radians, okay? So when you type sine of, let's evaluate this guy, negative 0.1, right? Highlight slash over negative 0.1. Look what I got. This is the result if you work in degrees, but make sure you work in radians. This is the one I was looking for, 0.998, okay? This was the first computation, right? Let's go ahead with the second computation. Now, since the second computation is very similar to this, I'm going to just copy and paste this here and add a 0 here, right? 0 here, add a 0 here. Aha, look what I got. 0.9998333, right? I need to evaluate now at this value. Aha, since the computation is very close to the previous, I just copy and paste. And this is one of the advantages of working with this decimal scientific calculator, that you can do this copy and pasting and just adjust as needed, right? Look, I need an extra 0 here, extra 0 here, extra 0 here. And look at this, another result, right? So let's write down these 3 results, right, that we got approaching to this function from the left, right? And then we will do the same from the right, right? And then we will see where we're headed. Let me just bring this down, hold it there, okay? So we got 0.9983 for the first computation. For the second computation, we got 0.99998. For the third computation, we got 0.9999. 998, right? Now we're gonna do it with these positive values. So I bring back my Desmo Scientific calculator, and notice these points or these input values are these input values, but without a negative sign, right? So all I'm gonna do is I'm gonna eliminate the negative sign, and I will get the new output values, right? And again, that's the advantage of working with our Desmo Scientific calculator, because you can do these things, right? Yeah, no, notice same, right? Same values here, same. It's because sign of negative x is minus sign of x, and the negative sign they cancel, right? So get the same value. So let's write them down, okay? All right, and then we will try to figure out where this is going. While I write this, try to see where the numbers that we got on the left and where the numbers that we got on the right are going, are approaching. Try to figure that out, right? To put it simple, where is this going? Where this is going? Can you figure this out? Anyone? Let's see. Oscar, good thinking, good thinking. You're good at pattern recognition. Very good, which is a very, very good skill in calculus. Grace, very good. Adriana, great. Excellent, right? Very good, guys. You're gonna do this in your homework. Try to remember. Yeah, so clearly, when we look at our output values here, when we approach from the left, these decimal numbers are clearly going to 1, right? Going to 1. Approaching, closer and closer to the real number 1. Same on the right side. If you approach to 0 from the right, these decimal numbers are also going to 1. Convergence, look, from the left going to 1, from the right going to 1. Therefore, conclusion, the limit of sine of x over x as x approaches 0 should be this guy, right? 1, because there is a convergence. And I want you to remember this result, guys. It's a very important result. This is a very special function, right? And remember, limit of sine of x over x as x approaches 0 is 1, okay? All right, now this is, there was a way for me to show you what is this method all about, right? The table method, right? You compute output values and you see if they are going from the left, from the right to the same real number. That is the limit. I want you to do this now on your own here, okay? To practice, try to do this guy. Can you try? We did it with sine, right? We did it with a different function. This one, number 2. They give you this function and they ask you to fill up this table, right, with output values and see where the output values from the left are going, where the output values from the right are going, right? The tables are pre-constructed here, so I would advise you just to pick, since we are going to 4, right, to this value 4, evaluate this guy, the closest, right, this and this. This guy, do the evaluation here, do the evaluation here, and see where they are going, right? If there is convergence, then you got the limit, right? So do that. Yeah, evaluate there. I think Sarah figured it out. Yeah, very good, very good. Yeah, excellent. Yeah, so yeah, it's a little bit tricky because there are a lot of computations needed, but again, as a hint, just take the closest values to 4, right? From the left, 3.999, from the right, 4.001. Yeah, I see more students posting answers. Grace, yeah, great, excellent, Grace. Yeah, you got it, Use your calculator, right? Yeah, make it a little bit bigger. Yeah, great, guys. So, let's take a look at this. All right, so if we use our calculator, we're supposed to evaluate our function, this one, at values very close to 4, but not at 4, right? Because if we evaluate at 4, it's impossible. 4 minus 4, 0, square root of 4, 2 minus 2, 0, 0 over 0, undefined. So let's evaluate it at this point first, and then at this point, okay? So first evaluation should be, instead of x, you write 3.999, 3.999. Then you do minus 4. You can use this fraction form, but I often just highlight a slash, right? And then a square root of x, the square root function is here, a square root of 3.999, remember? That's the input value. Come out of the square root, minus 2, right? Gives me this value, right? 3.9997. Excellent. All right, that's the guy that we're going to write down here, right? But besides this guy, there is another evaluation here. Same as here. I'm going to copy and paste. But I'm going to change the input value. This is no longer the input value. The new input value is 4.001, right? This guy. I'm going to erase this guy. I'm going to write instead 4.001. This is if you use the Desmos scientific calculator. If you're using a regular calculator, you can do that too, right? I think it's possible. Yeah. Yeah, but I just look at these two results, right? This guy goes here, this guy goes here, right? Let's write them down. Let's write them down. And then let's make our decision, right? This guy, when evaluated, right, is giving me 3.99975 rounded. And this guy, when evaluated, is given 4.00205. And it is clear that from the left and from the right, we are sandwiching between quotations, right? The number 4, right? The number 4. So that is the limit. That is the limit, right? So excellent, guys. So this is 4, right? Follow? 4. That's why this is it. Limit is 4, and that's the table, right? To these guys, hint, they are asking you to compute the limit of this function, cosine of 6 theta over theta, as theta goes to 0, as theta approaches 0, right? And hint, focus on values that are really, really close to 0, these two, right? 0 is in between. So because of that, try to output the value for this input value and try to get the output for this input value and see if there is convergence, right? If the output values are going to the same real number. In case they are not, then you just have, you know what to say, right? You will say that the limit does not exist. But in case there is convergence, that number, that real number should be the limit, right? So go ahead and try this, Evaluations here and here, that's the hint. And then we'll go over infinite limits. Yeah, let's do number 3. And the hint again is evaluate, do the evaluations at this value and this value, also in radians, right? Don't forget, in radians. Yeah, maybe I should write, make sure, note here, make sure your calculator is working in radians. Note. Make sure your calculator is set to work in radians. It's tricky, the question, right? But doable to work in radians. Yeah, I'm gonna use my scientific calculator. In case you were not here when I share the link, here is the link again. Or just go to our website or to Blackboard, the link is there. This is the scientific calculator I'm gonna use, and you can use this also when you take your exam. All right. Okay, let's do it together, okay? It's very tricky. If we do the evaluation at this value, we have to do cosine of 6 theta, right? 6 theta. Theta is in this case negative 0.001, right? I'm gonna write it within parentheses. When you write this within parentheses, it will multiply the number 6, right? Now that's for the numerator, right? For the denominator, a slash, and the denominator I have to write theta again, but theta is this guy, negative 0.001, right? And now this is in degrees. I want this in radians, right? Make sure, remember, I wrote a note here, make sure your calculator is set to work in radians. Radians, right? Look what I got. I got this value negative 999.98, right? Yeah. Now I need to do another computation. I hit enter. I need to do the same computation, similar. It's just that the input value now doesn't have this negative sign, right? It's 0.001. So let's copy and paste this here. And let's just remove the sign, right? Just remove the sign, right? That's all it takes. And you see this, right? Now, in your opinion, guys, from the left, this computation is going to negative 999.98, a negative number, and very, very negative. From the right, I'm going to a very, very high number, positive 999.98. In your opinion, does the limit exist? Anyone? I see. Oscar, yeah, you got it. Yeah, it's the limit does not exist, does not exist. DNE, Grace also, bro. No, DNE. Yeah, excellent, excellent, guys, right? Because in one hand, we're going to negative 999.98. I will write it down here. And right now, the evaluation here was saying this guy, negative 999.98, I believe, right? And the other was 999.98, I think, right? Something. This is positive, going up to infinity, right? Growing without bound. This is decreasing without bound. This is going in this direction. This is going in this direction. They will never meet. So in that situation, you say limit does not exist, D, right? Be careful there, guys. Sometimes there is convergence. Most of the time, I would say, but sometimes in some weird cases, there is no convergence, and this is what happens. Now, if you want to see this through a graph, right? Because sometimes it's good to see this from different perspectives. Let's say, what will happen if I graph this guy? Let's see. Let's check in our Desmos graphing calculator. Cosine of 6 theta. Theta is the same as x, right? So let's write x, 6x, and all that over x. Look what is happening here in the graph. Notice. In the graph, if you approach from the left to 0, you are going down to negative infinity, right? On the right, if you approach 0 from the right, you're going up. You're going up to infinity here, you're going down here to negative infinity. They will never meet, right? There is no convergence. That's why the limit does not exist. The limit does not exist, right? Yeah, good, good, good. So we confirm this with the graph. So in mathematics, everything has to make sense. Look at it from different perspectives, right? Confirm your knowledge, guys. All right. So, but this kind of introduces this idea of there are cases where sometimes these computations, they lead to very, very negative numbers, such as negative infinity, or very, very big positive numbers, such as positive infinity, right? So this leads to this idea. So this is why mathematicians define what they call infinite limits, right? Sometimes the limits might not be real numbers, but instead symbols like plus infinity or minus infinity, right? So let's talk about that. Here it says, right, let's consider the graph of this function that you might have seen in pre-calculus, f of x equal 1 over x. It is called the reciprocal function, right? It's one of the parent functions that you might have seen in pre-calculus. This guy is called the reciprocal function. The reciprocal function. And this reciprocal function, when graphed, will show the following shape. Positive part here looks like this, right? And you've done this in pre-calculus, right? Yes, it is. And over here looks like this. Professor, what is this? The graph of this? Guys, I said, right? If you don't see this clear, use your tool, the grapher, right? The Desmos grapher. It's going to help you to visualize this. 1 over x. Look at this. You see? Here, here. Now, when you use this tool, guys, you got to be careful. I said, right? It's a basic grapher. Notice the curve here never touches y-axis. The curve never touches x-axis, right? Here in the Desmos grapher, it looks like it's touching it, right? But it's not. In reality, it's not, right? If you enhance, if you zoom in, you will never see them meeting. You see? Never. Okay? So be careful with those things, guys, okay? Use this as a tool to help yourself out, but you have to check your knowledge with this tool, right? They never meet. Okay, but this is the graph. Now that you have this graph, what would be the limit as x approaches 0 from the right? Right? Well, if I'm approaching 0 from the right, then I'm going in this direction, considering the input values, but the output values are going where? Well, notice they are growing and growing without bound, right? Up. So this is what mathematicians call positive infinity, right? You approach 0 from the right, the output values are headed to plus infinity. So they will say this plus infinity, or simply infinity. You're allowed to drop the positive sign, right? Now, what will be the limit of 1 over x as x approaches 0 from the left? Now, from the left, well, then you gotta go this way, input-wise, output-wise. However, we are going in this direction, right? The output values are negatively growing, negatively, I see within quotations, right? They're becoming more and more negative. That's a better way to say it. So they are going to this guy, negative infinity here, right? So mathematicians say limit of 1 over x as x approaches 0 from the left is equal to negative infinity. Conclusion. Notice, from the right, I'm going to positive infinity. From the left, I'm going to negative infinity. They are not the same. Just like an example I showed you before, right? In one hand, you're going up. The other hand, you're going down. No convergence. This means that this has to be DNE. Does not exist. Does not exist, right? Yeah. Very good. Great. Now, let's consider this other graph now. Very close to the previous, but the difference is now that this guy is square. It's the reciprocal function here, but it's squared, right? 1 over x squared. If you graph this function, this part will remain the same because x is positive, nothing changes, right? But this part that was negative because of this square will be reflected up here, right? Was reflected up here. As a result, you're gonna get this. It's gonna look like a volcano, like this. Right? Professor, what? Volcano? Well, if you don't recall this from pre-calculus, you can graph it, right? We have over to 1 over x squared. the volcano is there, right? And as I explained to you before, it seems like they meet, but they never meet. If you zoom in, you will see that they never meet in reality, right? So be careful there. Yeah, so is the volcano there that we have here, right? Now, to find the limit, then you have to trace the graph, right? If you approach 0 from the right, you are output-wise going up here, right? The output values grow and grow without bound, headed to positive infinity. So this will be positive infinity. Now, if you approach 0 now from the left, before we were going down, but now since this is square, you still go up, right? Still going up to positive infinity, right? If you approach 0 from the left. So this one also plus infinity. Now there is convergence. From the right, I am approaching positive infinity. From the left, I'm approaching positive infinity. Since these two guys are the same, mathematicians as a conclusion, they write that the limit of 1 over x squared as x approaches 0, simultaneously, right, from the left and the right, is positive infinity, right? So be aware of that, guys. Right? Very good. Now, one thing that mathematicians notice is this. If you look at the exponent, if this guy is even, this is positive infinity. But if this guy is odd, remember there is an invisible one here, odd, this guy is undefined, does not exist, right? Yeah, so then they said, okay, then let's take these two guys, these two graphs as our basic graphs, and let's extend this result this way. In general, if you are given a function like this, 1 over x minus a raised to n, where n is odd first, then the graph of this will have the following shape. It will resemble what we had before, right? This way. But there is a shift here, a units to the right, a units to the right. So a will be here. You shift your graph to the right, a units, right, if a is positive, and you will get something like this, right? So, but the shape is there, it's the same, right? So if n is odd, then the limit as you approach a from the right will be still positive infinity, right? Look, notice going up, positive infinity. And if you take the limit of this function as x approaches a from the left, it's still you are going down here minus infinity. This will be minus infinity. And as a conclusion, the limit will not exist, right? So now for the other case, if n is even, such as 2, remember, the graph of this guy will resemble a volcano, right? We'll have the following shape. A shift to the right, remember, is opposite to whatever you see here, right? A. And the volcano will appear there like this. So if you are taking the limit of this function as x approaches a from the right and n positive, then you will end up going output-wise up here. This is plus infinity, right? This is plus infinity. And if you approach from the left, the same, because it's still, since the exponent is an even number, such as 2, 4, 6, 8, still up, so plus infinity. So since there is convergence, it means that this will be positive infinity, right? So these properties, guys, will help a lot when you figure out infinite limits. How? Well, for example, look at this. Before we go to the worksheet, let me show you some examples. Example 1, compute the limit of this function 1 over x minus 3 squared as x approaches 3. As x approaches 3. All right, so notice the graph of this guy is the graph of the reciprocal function 1 over x shifted 3 units to the right, right? So you go from the origin, 1, 2, 3. there you're gonna work with this volcano-like function. This is even. So the graph of this will resemble this volcano, right? And there you say, okay, then what is this limit? Well, limit as x approaches 3 simultaneously from the right, from the left and from the right of this guy, 1 over x minus 3 squared will be equal to what? Well, from the right, you're going up here towards infinity, positive, right? But also from the left, you approach 3 from the left, you're going up here, right? Positive infinity. So this should be just positive infinity, right? All right, or just infinity. You are allowed to drop the positive sign, right? This is for the case of the exponent being even. For the case when exponent is odd, look at this. This now is odd, right? Then you want to work with this other shape. Remember, for exponent odd, the graph, after this shift, which means shift this graph 1 unit to the left. Remember, this is counterintuitive, the horizontal shifts, right? Counterintuitive. So 1 here shifted to the left. 1 to the left here, right there. You will see this shape, right? Remember? There we go. And now I want the limit as I approach -1 from the right. This is going where? From the right, this is going up to positive infinity from the right. From the left, I'm going to negative infinity output wise, right? No convergence, they're going to different destinations, right? So conclusion, then you will say that the limit of 1 over x plus 1 raised to the 5th power as x approaches to -1 from the left and from the right simultaneously does not exist, DNE, right? Because these two guys are different. Very good, very good. So probably we should practice now. Can you figure this out, guys? Number 1 first. Find the limit of this function, whose graph is this, as x approaches 5 from the left. Can you figure this out? And then you're supposed to figure out the limit of the function, whose graph is this, as x approaches 5 from the right. One-sided limits, right? Yeah. So hint for the first one, from the left, use, this is 5 here, so use this, right? Try to see where this is going. And for this guy, the hint, try to see where this is going. And then make your conclusion, right? Adriana, very good. Grace, Oscar, Sarah. Excellent, guys. Yeah, very good, very good. Yeah, I see. You guys figure this out. CG, also good, good, excellent, excellent, very good, nice. Yeah, know how to see that if you approach 5 from the left, right, this is going to negative infinity, right? It's decreasing without bound, so negative infinity. And if you approach 5 from the right, the output values are increasing without bound towards positive infinity, right? These two, excellent. So negative infinity first, followed by positive infinity. That positive sign you can drop. So this is it. Excellent. Great, 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 guys. So now number 2. Can you try a lot of? Yeah, this number 2 is very similar to number 1. So let's go over something different. This one's better. Yeah, try this, and then we'll move on to the numerical ones. Try this, do this one. What is the limit of the function f of x whose graph is this as x approaches the number 3, as approaches 3? And the hint again, try to approach 3 from the left, see where the output values are going, and then approach 3 from the right, see where the output values are going, right? And if there is convergence, there is a limit. If there is no convergence, no limit. Very good, Grace, CG, Oscar, Adriana. Yeah, very good, guys. Very good. Excellent, right? Yeah, clearly this is going to negative infinity. When you approach from the right, positive infinity. They're not the same. So conclusion does not exist, right? Does not exist. Excellent. Yeah, so great. Now the numerical ones, right? Let's try this without the graph now. Let's try to do it without the graph. Remember, it's not that hard. There are just two scenarios, right? Which one scenario is when the exponent is even, the graph should look like a volcano. The other scenario is when the exponent is odd, the graph should look like this, right? One over here, one over here. Yeah, try to do that and figure out the answer for, let's say this one. Number 5. Let's see. Ruby. Very good. Excellent. Number 5. Yeah, excellent. Yeah, Grace, also good. Very good, guys. CG. Good. Yeah, for this question, they're not giving you the graph. But remember, depending on the exponent being even or odd. Sarah. Yeah, sure. Very good. Yeah, excellent. Let's explain, right? We don't have the graph, right? But remember, we explained that if this exponent is even, that's just 2. Number 2 is even. Then the graph of this function should resemble a volcano, right? Yeah, very good, Sarah. Very good. Yeah, very good. Yeah, guys, always try as it was what is important, right? Great. Yeah, so since this is even, when you graph this guy, what's going to happen is that originally this is the graph of y equal 1 over x squared, right? But there is a shift here, shift of 7. So this is telling you that the graph just moves 7 units to the right. 1, 2, 3, 4, 5, 6, 7. 7 units to the right. So horizontal shift. So this is the new graph. Is the volcano shape still there, right? But this is now the graph, right? So now in here, if you approach from the left, you are going up to plus infinity. And if you approach from the right, you are also going to positive infinity, right? Positive infinity, they're saying approach from the right. So positive infinity. Yeah, they didn't want they didn't want you to approach from the left. So let's erase this so nobody gets confused there.
I'm sorry, Professor. Like,
sure.
Like when I first saw that question, find the limit, right? I thought
Yes.
I had to input use the table format. I didn't know it was for infinity. So I was thrown off and I wasn't getting the right answer. So like if you're having a test or your homework, how would you know that, oh, this question is specifically related as infinity question or is the type you have to use table? Are you going to specify the instruction, or we just have to guess? That's why I got it wrong.
It's a very good question, Sarah. How to know that this has to do with this approach and not the table, right? First, you have to kind of remember that the form, look, 1 over something is square, something raised to the first power, or maybe something cube, right? This form, that's why we explained that these properties, right? You see the form here, Sarah? Look, you see here, when n is even, this is what we have to use, right?
Yeah, okay.
Yeah, kind of try to remember this form, 1 on the top, and this binomial is square to some exponent on the bottom. And this is related to this part, this formula, right? Because with a graph, you can trace it quickly, right? I understand that the table also is an option, but it's not going to be very clear, right? Where you are headed, right? Where you are going, right? Because the numbers are going to keep growing and growing and growing, right? You understand? Like with a table, for this form is kind of, yeah, because you might have tried and the table were giving you very big numbers, right?
Yours. Yeah.
Yeah, and to the point that probably your calculator was showing your output using scientific notation, probably, right? Because it didn't even fit on the screen of the calculator, right? Yeah, that's the problem with using the table for this form. So for this form, it's better to use the graph, right? The graph. Yeah.
Thank you.
Yeah, good question, Sarah, right? And guys, if you have problem remembering the properties, graph it, right? Look, graphing it, what will you get? Y equal 1 over x minus 7 the square, right? Yeah, just be careful with the parentheses there. It is possible to graph this, right? We have this tool. So it's square. You see the volcano, Sarah? You see it, right? There you go. So then it tells you that, you see, the graph tells you that if you approach this value 7 from the right, output wise, you're going to infinity because you don't see that this meet, right? So yeah. So guys, use your knowledge and use your tools. Put it in your toolbox, right? Graphing, basic graphic calculator, it can help, right? Help you to figure this out. But the table definitely, it can be done, but it would be tedious. It's better this way. All right, let's continue here then, guys. Try this now. This is a little bit trickier. What about this now? Figure out the limit, and again, I claim it's the same form because of the 1 on the top, something on the bottom, right? Yeah, great. Yeah, figure out the limit. I'm gonna write it bigger here. As x approaches -2 of 1 over is telling you to use the properties, right? To look at the exponent, right? I'm gonna give you as a hint. The exponent here is 1, right? 1. Professor, I didn't see a 1 there. Well, mathematicians don't write the exponent when it's 1, right? But it's an invisible 1 there. And on top of that, I'm going to tell you that this 1 as a number is an odd number, right? Odd. So odd. So use the graph that corresponds to 1 over x, right? And try to figure this out. Yeah, and anything that is not working, just let me know, guys, so I can give you hints or explanations as needed. I see. And try to remember these things for your homework too. It's homework related to question related to the homework will appear that are similar to this. Ruby for number 7. Excellent. Ruby, Adriana, CG, Grace. Very good, guys. Very good. Okay. Excellent. Oscar, I think. Yeah, great. Yeah, very good, very good. Yeah, it's tricky, right? It's tricky, but we just have to be careful. Look, they are asking us to work with this function. The exponent is odd. So I quickly think of the graph of this, y equal 1 over x, right? That graph is this, right? But there is a shift here. This means shift this graph 2 units to the left. Remember, these horizontal shifts, they are not intuitive, right? They kind of do the opposite here. So 1, 2 to the left, -2. So this has been shifted to the left this way. And then answer the question, right? What happens if you approach -2 from the left? From the left, notice you are going down here from the left to -infinity. And if you approach -2 input wise from the right, you are approaching +infinity. There is no convergence. No, they're not the same destination, right? So then you have to say does not exist. The limit does not exist, right? Yeah, very good. Now let me talk about, maybe we can do one more and then move on. Maybe we should do this one too, just to make sure that everybody's okay. Yeah, do this one, guys, and then we'll talk about the vertical asymptotes. Can you do this one? The one in red, the limit of 1 over x minus 9 as x approaches 9 from the left. I'm gonna write it here bigger. Figure out the limit of 1 over x minus 9 as x approaches 9 from the left. Professor, how do you know it's from the left? Because of this negative sign. Negative sign on top of the number means approach from the left. I see for number 4 students. ZG, good. Sarah, good. Grace, Adriana, Oscar. Very good, guys, very good. Yeah. It's just, there are just two scenarios, right? Either the volcano shape or this shape, right? And you just follow. Great, right? This guy, when graph is just this, the graph of y equal 1 over x, right? Which is this, but shifted 9 units to the right, The horizontal shift is counterintuitive, right? We know that from pre-calculus. So 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere there. Draw a vertical line, and there, this has been shifted. So it's like this. And there you answer the question, right? They want the limit as x approaches 9 from the left. So we do the trace here, right? Trace the output values here from the left, approaching the 9, right? And they are clearly going to -infinity, right? -infinity. So this one, okay? Very good, guys, very good. This one I will let you do at home, okay? Try this one at home. Let's talk about these guys now. Find all vertical asymptotes of a given function, okay? Vertical asymptotes. Okay, so let's go back to the lecture then. Mathematicians studied these infinite limits, right? And they saw this behavior, right? The curve going up to infinity, the curve going down to infinity, right? So they came out with this definition to capture this behavior of these curves, these functions when graphed. It's called a vertical asymptote. And turns out limits are good to define formally, mathematically, these vertical asymptotes, okay? So let f of x be a function if any of the following conditions hold. The line represented by this equation x equal a, right? A is some real number, is a vertical asymptote of f of x. And those conditions that they mentioned here are this. Limit of the function f of x as x approaches a from the left is positive infinity or perhaps negative infinity. Limit of the function as x approaches a from the right is positive infinity or perhaps negative infinity. Or limit of f of x as x approaches simultaneously from the left and from the right equal positive infinity or negative infinity. Okay, if any of these conditions holds, then you got yourself a vertical asymptote. okay? So let me give you an example here before we go over the worksheet. Example 1 says, find the vertical asymptote or asymptotes of this rational function 1 over x minus 3 raised to the 4 power. All right, so notice, right, that this function, when graphed, is going to show a volcano shape. How do you know that, Professor? Well, because of this is even, right? And it will be a shift of the graph of the function 1 over x squared, 3 units to the right, right? And 1, 2, 3, let's say 3 is there, right? So the volcano will appear there, right? And clearly you can see there the vertical asymptote, right? But how can we formally catch this vertical asymptote without even graphing? Well, we can take the limit, right? Knowing that at x equal 3, the function is undefined, we can take the limit. Let's write it, it's important thing. At x equal 3, the function is undefined, right? Therefore, this gives me the hint, right? What happens if I take the limit as x approaches precisely this guy, 3? Uh-huh. 1 over x minus 3 raised to the 4 power. What would be the limit of this? Someone wrote something on the chat. Oscar is asking, how do we know that at x equal 3, the function is undefined? Oh, you got it already. Yeah, it's because if we, maybe I can write a note. Yes, it's important to notice between parentheses, right? Notice. If we evaluate at 3, we're going to get ourselves in trouble because this will be 1 over 3 minus 3, 0, 0 to the 4, 1 over 0. This undefined, right? Yeah, this is another way to see it. It's basically the opposite of this, right? Sometimes students ask me, Professor, how do you know that you have to take the limit as x approaches 3? Well, because 3 is the opposite of this. Yeah. Opposite of this. Opposite, always. If I had x plus 3, I have to take the limit as x approaches minus 3. So opposite, right? Very good. Opposite. Yeah. Okay. Yeah. But now, if you take this limit, right? If you go here, as x approaches 3 simultaneously from the left, from the right, right? You know, you see this behavior, right? From the left, where the output values are going. They're going to positive infinity. And from the right, also, they're going there, right? Positive infinity. So I got this result, right? That this is positive infinity. It's pretty green. This convergence, right? Positive infinity. I fulfill one of the conditions, right? Maybe I should write this in. Look, this statement is one of these 3 statements that I wrote here on the top. Is plus infinity as x approaches to this. As long as you fulfill one of these, then you have the right to claim that that's an asymptote, the vertical asymptote, right? So therefore, then you can say then vertical asymptote is defined by this equation, x equal, and you take again this guy, 3, right? So that's how you find your vertical asymptote, which is this guy, right? This guy. Is a line, a vertical line, showing this behavior related to the graph. The graph gets closer and closer to it, right? To the line, never touching it though, right? Never touching it, as you can see. Gets closer and closer, never touching it. That's the vertical asymptote. Now, guys, notice I use limits, right? Calculus to figure out the vertical asymptote, right? But that's very tricky, very complicated because I had to go to the graph and then I had to figure out that this was the opposite of this, right? It's very tricky, right? So there is a shortcut. There is a shortcut to do this using algebra, but for some certain type of functions, which are called rational functions. And here I'm gonna give you this as an alternative, right? You can use this method with limits, right? But remember, it's a little bit tricky by satisfying one of these three statements, right? Or you can use this other method that I'm gonna give you as an alternative whenever your function looks like this, like a rational function. Polynomial function on the numerator, polynomial function on the denominator, okay? Look, alternative for rational functions of the form f of x equal p of x, some polynomial here, and over q of x, some other polynomial here, to find the vertical asymptote or asymptotes. There may be more than one. Step one, simplify. Maybe I should write here as step one, simplify. Step two, set the denominator equal to 0 and solve for x. Remember here, isn't it true that if I take this denominator, x minus 3 raised to the 4, and make it equal to 0, isn't it true that when I solve it, I will get x equal 3? But turns out that x equal 3 is precisely the equation of the vertical line associated to the vertical asymptote, right? So it's like a nice alternative in case it's too complicated for you to think of limits to find the vertical asymptote. Here is an example before going over the worksheets, which is going to help you also in your homework. Find the vertical asymptote or asymptotes of this rational function, 3x over x squared minus 5x minus 24. I can do it using limits, but remember, for that, it's very tricky to figure out what you're going to write here, right? So instead, I'm going to follow this alternative here. To follow the alternative, what I'm going to do is this. I'm going to factor the denominator, okay, to see if I can simplify this first, this expression, okay? Factoring this guy, x here, I need two numbers whose multiplication is negative 24, whose sum is negative 5. Those two numbers, after some trial and error, are 8 and 3. I want the sum to be negative 5, so the one dominant in value should be this guy, right? So 8 negative, this other guy positive. This is the factorization of this, right? Yeah, factoring this. And I can see that nothing gets simplified. So the, yeah, very good, Adriana. Yeah, we're going there. Yeah, Adriana, Samantha, Sarah, sorry. Sarah, you figure this out, right? Yeah, great. Now, once it's factor simplify, so this done, right? Always simplify first. Step 2, set your denominator equal to 0 and solve for x. So let's set our denominator, which is this guy, x plus 3 times x minus 8, sorry, equal to 0, meaning x plus 3 equals 0, or x minus 8 equals 0, right? Set that equal to 0. From here, subtracting 3 on both sides, I get that x equals negative 3. From here, adding 8 to both sides of the equation, I get that x equals 8. Turns out, guys, these are the vertical asymptotes. Vertical asymptotes are given by these two equations, x equals negative 3 and x equals 8, right? Yeah, as some of you guys already figure out. Excellent, excellent, Sarah, excellent, Adriana. Yeah, that's what it is. Now, it's possible to get them using limits, but again, guys, for that, you have to take limit as x approaches -3, limit as x approaches 8, and figure out that those are equal to plus or minus infinity, right? Which is a little bit trickier, I think. So consider this alternative in case you cannot get this done using limits. So let's go back to the worksheet, right? To finish this up. And one way or the other, try to figure out these two. First, number 8, please go ahead. Either with a shortcut or with limits, right? It's up to you. Try to find the vertical asymptote there. Grace. Very good, Grace. Yeah, you made my day. Excellent, excellent. Yeah, not that difficult. Yeah, Grace, CG. Yeah, very good. Yeah, there is one more answer. Yeah, Sarah, I think you have to adjust, but don't feel bad about it because, yeah, now better. Yeah, we'll see. We'll see together. Yeah, this worksheet, guys, are for you to try, okay? You don't have to be right all the time. You can try. We are learning here together, right? Yeah, so let's say they want your vertical asymptote here, right? If you want to do it with limits, you're supposed to take the limit, remember, as this guy goes to the opposite of this, right? Opposite, opposite. And then you are supposed to verify that this is either plus or minus infinity. In this case, it's not so simple here because the graph is not even clear, right? If you take the graph, if you graph it in your scientific calculator, 3x over x plus 4, look, this, right? We are trying to figure out what happened at -4. -4 is here. You're approaching from the right, going to infinity, from the left, going to infinity. This is enough to say that this is a vertical asymptote, right? You see it? Yeah. So you go from the left, positive infinity, from the right, negative infinity, right? So therefore, let's say you go from the left, right? So it was down, positive infinity, right? So this tells you that yeah, that this has to be an asymptote, right? X equal -4. But if it's complicated this for you to grasp, right? It's difficult with the limits, right? Use the shortcut that I gave you, the other approach, right? So alternative, set, simplify first. Clearly this is simplified, right? Nothing to simplify. Set denominator equal to 0, and it will come out there. It will come out there. X equal -4 is your vertical asymptote as we shown with the graph and taking limits, right? So this guy. Try to do this guy, please, to finish this up. I'm gonna give you a hint for this one. Factor this, right? Factor. And let's follow the approach, the second approach. Factor. Difference of squares, right? I think it's this x squared minus 36, 6 squared. Yeah, factor using difference of squares. Of squares. Can you see? Oscar, yeah, Adriana, very good, guys. Excellent, excellent, excellent. Yeah, this one, it would be crazy to do it with limits because you will have to take 2 limits. But with the strategy that I show you with the alternative, Grace now also good, right? Grace, Sci G also good. Excellent, guys, excellent. I'm glad that you are picking up this. Yeah, so if you factor, this is clearly x minus 6 times x plus 6, right? nothing to simplify. Be careful, right? If this were a 6, maybe you can simplify this and this, but it's a 2. So there's nothing to simplify. So it's already simplified. Step 2 says set whatever your denominator is after you simplify, right? After you simplify, very important that word simplify. After you simplify, you set this equal to 0. And from there, you can get your 2 vertical asymptotes. 0, 0. X equals 6. One vertical asymptote, shorthand for vertical asymptote, VA, okay? So I'm going to write as VA, vertical asymptote, X equals 6. And from here, minus 6, X equal minus 6 will be the second vertical asymptote, okay? Yeah, great. These are the 2. Now, let's say I'm going to be 100% sure before I choose my answer, this, right? Let's graph it. And let's see if indeed these are the 2 vertical asymptotes, right? You see, y equal x plus 2, x plus 2. To keep the denominator all together, highlighted, slash, right? There might be other ways to do that, but that's one good way to do it, minus 36. Look at this, guys. Here is where this guy is, x equals 6, right? And I can show it to you, x equals 6. No, x equals 6, 5, I wrote. Aha, this is one of the asymptotes, this one. Vertical asymptote, and the other one, x equal minus 6. Where is that? Aha, the other asymptote, you see? This is this asymptote, this vertical asymptote, this is the other vertical asymptote, right? So it makes sense, everything is good, right? Graphically, computationally, right? Algebraically, everything matches. When you do your Maple labs, they want you to do this kind of things, okay, guys? Try to remember that. They want you to show these limits, this is continuities, later we'll talk about that, but following the graphic approach, you do this, in Maple, of course, or following the table approach, you use the tables, or following some other approach, right? So you just have to show it in different ways, okay? All right, I think there is no time for more. So let me just